Hello dear students, welcome to online class. I am Jinder Joseph from Ravila Academy Vidyashram. See, I hope you all are safe in home, be in home, be safe. Okay. Already we have started our 12th standard physics first chapter electrostatics. In the previous video we were discussing about Coulomb's law, first charges, Coulomb's law, after that superposition principle and its all problems. Right? So this is the third video. Next topic, important topic, electric field. Electric field, in this section we will discuss electric field, what is the concept, what is the definition and all, what is the concept, what is the definition for this electric field, then its important aspects, right? And only one problem. This section we will discuss only one problem based on this electric field, because next video I am including only problem. That whole video, that whole video we will discuss only numerical based on that electric field. So for getting the concept, listen this video, watch this video till end, build your concept, build your future, right? So starting the concept of electric field, what is electric field? So in the previous section we were discussing about, consider you are having a positively charged particle plus q over here, you are having a positively charged particle plus q. So if you are keeping another charge, we consider it is a plus q naught. Right, I am writing the charge is what? Plus q naught. Positively charged particle. So if you are keeping two charged particles at a distance, what will happen? Definitely force of repulsion will be there because it is unlike charge. So the question arises, question comes, how this charge knows the presence of the other charge? How this charge knows the presence of other charge? So what I am doing, I am covering this charge. But this charge will know whether you are covering or not. This charge will know the presence of the other charge. Question, how this knows? So this concept, electric field concept, is introduced by great Michael Faraday. So he was saying that in the universe, all the charge particle creates its own field. All charge particle in universe creates its own field around it. Ready? All charge particle in the universe creates its own field around it. That means for this charge particle, it creates its own field. It creates its own field around it. Ready? So if any other charge particle come to this field, comes to this field, experience a force. So you just imagine, in a city, one dawn is there. This is our dawn. Right? So this area is completely under the control. This much of area. This whole area is under the control of this dawn. So what will happen? Consider another dawn or another person. If anyone is coming to this area, will experience a force of this dawn. Right? That means this dawn can exert a force. This dawn can exert a force on the coming persons. So here consider a positively charged particle. Now this is not dawn concept. This is what concept? It's a charge concept. Consider you are having a positively charged here. This positively charged particle creates its own field around it. If any other charged particle comes to this field, experience a force. If it is a positively charged particle, this field is, radially away. This field is moving away from the charged particle. And if it is a negatively charged particle, you are keeping a negatively charged particle, this field is getting into the charged particle, coming to this charged particle. For a negatively charged particle, field lines are what? Into the charge. For a positively charged particle, field lines are moving away from charge. So this charge creates its own field. Dawn. Right? So this charge, we will say what charge? Our source charge. This charge we are writing as what? Our source charge. Right? So keeping the next charge. So we are checking whether the electric field exists or not. We are testing whether electric field exists or not. How to check whether there is any electric field? You just keep one small charge, one small positively charged Q0. So very small charge, positive charge. You are keeping a very small positive charge. We are calling that charge as test charge. So what is test charge? In order to check whether in a place there is any existence of electric field or not. So that we are keeping the positively charged, positively test charge. Test charge is too small, that is a concept. Positive test charge is always positive and it's a very small magnitude. It won't create its own field. So some students will ask, sir, here it creates its own field, so definitely this also will create its own field. No, it is a very small charge, a theoretical concept only, so that it will not create its own field. It will not manipulate or it will not affect the field of this source charge. Right? So how can we define an electric field? So in universe, any charge particle creates its own field around it. If for a positively charge, it is moving away. For a negative charge particle, electric field is coming into the charge particle. If any test charge is placed in this field, experience a force. Any test charge placed into this field experience a force. Ready? So simply what we can say, electric field, it is a region around a charge. It is a region around a charge in which other charge particle experience a force. Another definition. It's quite too hot. Ready? So electric field is a region around a charge in which other charge particle experience a force. Another definition. Any definition you can write. Right? So first definition what I said, all charge particle in universe creates its own field around it. If any charge particle come to this field, experience a force. Or an electric field is the region around a charge particle in which other charge particle experience a force in that field. Ready? That is about what? Electric field. Now we are discussing its important aspects. First point, this point. For a positively charged particle, electric field is moving what? Radially outward. And for a negatively charged particle, it is radially inward. Electric field is coming radially inward to the charge particle. Radially inward. Alright? So listen, consider this point P. Question, I am asking, draw the electric field at this point from this charge particle. So always for drawing the electric field, we will draw the line joining. Always line joining. So question, electric field can go in this direction or electric field can come in this direction. Question, in which direction electric field will be? Electric field for a positively charged, it is moving radially outward. For this charge point, it is moving away radially outward. This is the direction of the electric field due to this positively charged. Say consider a point P over here. Now just connect. Right? So question, what is the direction of the electric field at this point? What is the direction of electric field? Since it is a negatively charged particle, don't draw like this. Wrong. It is radially inward. Radially means perpendicular to this point. Radially. So for a negatively charged particle, it is moving into the charge. For a positively charged particle, it is moving away from the charge. Right? First aspect, what? Positively charged, radially outward. What? Electric field is radially outward from the charge. Negatively charged particle, it is radially inward to the charge. Second point number 2. Ready? Then electric field, it is represented by, electric field we will represent by the letter E. Electric field we will represent by the letter E. Question, how to find electric field? How to find electric field at a point? You need to find the electric field at a point, right? Listen. So consider, you need to find the electric field at this point. Electric field is represented by E. Electric field, what is the magnitude you need to find? So this is the technique. In order to find the electric field at a point, what do you need to take? Take a point charge. What? First step, take a point charge. What a test charge, Q naught. So in order to find the electric field at a point, take a test charge. This is a test charge. So I need to find it B, then move to B. This is a test charge, test charge, test charge, test charge. Keep that test charge at this point. Test charge. So keep the test charge at the point where you need to find the magnitude of the electric field. Right? So next you need to find the force on test charge. Force on, so I am writing it over here. I need some more space so that we can discuss with the positively charge, negative charge also same. Ready? So in order to find the electric field strength, what I told, go with a which charge? Source charge or test charge? Who is creating field? Source is creating field. What you are for testing, what you are keeping? A test charge. So in order to find the electric field strength at a point, you are going with a test charge. At that point you are keeping the test charge. So electric field strength is given by force on test, not a phone. Okay. Force on test charge divided by test charge. What is the equation? Electric field, magnitude of the electric field is given by force on test charge by test charge. We can find what is electric field. Force, if two charge particles are there, which force? Coulomb's law. What is Coulomb's law? 1 by 4 pi epsilon 0 K. Isn't it? 9 into 10 to the power 9. K into Q1 plus Q. Q2, Q0 by, let this distance is R. So R square. K into Q0 by R square into unit vector. Since it is an electric field, is a vector quantity, one direction is there. So we need a unit vector. In which direction? That direction. Right? So K into Q0 by R square. So that is the force on test charge. All divided by test charge. What is test charge? Q0 is test charge. This source. So what will happen? Q0 will come here. Q0 cancel. So electric field, and writing electric field magnitude is equal to 1 by 4 pi epsilon 0 Q. No, 1 Q is enough. Q by R square into unit vector R. Electric field is equal to KQ by R square into unit vector R. Say in order to write in vector form, this is what unit vector. In 11th standard we have discussed unit vector. We can write a unit vector R cap. We can write it as what? Original vector by mode vector. Unit vector is equal to vector by mode vector. Original vector by mode vector. Unit vector equation. So we can write that equation KQ by R square into vector. Instead of this unit vector, I am substituting R vector by R, which is equal to KQ by R cube into R vector. See, this equation is also correct. KQ by R cube into R vector. This is R vector, this is unit vector. If you are using unit vector, it is divided by what? R square. Right? That is the next point, electric field. So how to find the electric field strength? Electric field strength, for finding electric field strength, you need to keep the point charge. Right? Keep the point charge at that point. Not point charge, test charge. Keep the test charge at that point. Force on test charge by test charge. Force, Coulomb's force divided by test charge. Test charge Q0 cancel. So the equation KQ by R square. This is the vector equation. KQ by R cube into R vector. Right? So second case. So the definition for electric field is ready. Definition for second point I am writing here. Electric field at a point is equal to F force by charge. Electric field at this point, what I told, electric field in this equation, electric field is equal to force on test charge by test charge. Electric field is equal to F by Q. Since electric field force is a vector, scalar, so electric field is a vector. From here we can say the direction of electric field is same as direction of force. Direction of electric field is same as direction of force. That is also keep in your mind. Yes, fine. Ready? So from here we can say the force acting on a charged particle in an electric field. From here we can say force acting on a charged particle in an electric field F is equal to EQ naught. If it is a 5Q, E into 5Q, whatever it is, you can use this equation. F is equal to EQ. F is equal to EQ. Electric field strength into test charge. Or whatever the charge, no problem. In an electric field, if you are keeping 5Q plus 5Q, minus 5Q minus 5Q direction, you need to check. So next point. Ready? Next point. Electric field at a point is independent of electric field at a point independent of test charge. It depends only on source charge. See, I told that Don case, right? So Don have a particular power. So whoever coming from the outside, Don, he is creating his own field, right? It depends only on Don, right? So it is independent of what whoever coming from outside. It is independent, doesn't matter. So only for electric field at a point depends only on source charge. It is independent of what? Test charge, right? Fourth point related to test charge only. This test charge, I told at starting, test charge is a concept only. Test charge should be too small. Should be small in such a way that it does not alter the electric field by this source charge. Test charge, it should be too small, because I told if you are keeping a charged particle, it can also create a electric field, but it should not be too big. It should be too small in such a way that it should not alter the electric field strength of this source. So test charge should be small in such a way that it should not alter the electric field of the source charge. Alright. Fifth point. Electric field is a vector quantity. Electric field is a vector quantity in space. At each point it has one direction and one magnitude. Two direction not possible. We can't go. We are going this way, so either I can go in this direction. I can't go in both directions. Similarly, electric field is a vector quantity in space. At a point it has a single direction and a magnitude. It is a vector quantity, right? Sixth point. What electric field is a vector quantity. Next, electric field, this equation. What is the equation for electric field? E is equal to 1 by 4 pi epsilon 0 Q, source charge by R square, magnitude. Magnitude of the electric field is given by kq by r square is only possible, is only applicable for point charges. Only applicable for point charges. Is equal to 1 by 4 pi epsilon k means 1 by 4 pi epsilon 0 9 into 10 to the power 9 Q by R square. Q is which charge? Is source charge, right? So it is only applicable for what? Point charge. If charge is distribution, if charge is distributed over some bodies, that is our next topic. If charge distribution comes, what is the electric field? We will discuss in next video. So that is this equation equal to 1 by 4 pi epsilon 0 Q by R square is only possible for what? Point charges. Then the seventh point, last point, uniform electric field. Two types of electric field. One is uniform and non-uniform. Non-uniform electric field. Uniform and non-uniform electric field. Consider in this side, say I am drawing the electric field lines like this. Consider if the strength of the electric field and direction, if the magnitude and the direction of electric field is same everywhere in a plane, we can call it as what? Uniform electric field. If the magnitude and direction of electric field is same, uniformly arranged, magnitude and direction, if direction is changing, finished. Wrong. So if both the magnitude and direction of an electric field is same in a region, we will call it as what? A uniform electric field. Then if magnitude, let us see, one electric field like this, one is like this, one is very small, and one is like this. See, this type of electric field we will say what? A non-uniform electric field. If the magnitude and direction of electric field is different, then we will say what? A non-uniform electric field. So the question is, a point charge produces which field? Uniform or non-uniform field? A point charge, I am giving a plus 2q here. It can create a field. Since it is a positively charged particle, why I am putting this arrow in outward? Because for a positive charge it is radially outward. Question, is it uniformly arranged or what, uniform field or non-uniform field? It is not out, it is what, non-uniform field. Why? Because here if I am drawing some more lines, this is the electric field. Actually electric field lines topics are there. That is also coming video. So when you are checking, see I am doing some more field. So now in this region, if I take in this region, this circle, two field lines are there, right? So if it is going some more distance, if I am taking the same area, see only one field. That means as you move away from this source, see Don is sitting in his palace. So that palace will be completely under the control of Don. Just to be, out of the palace, he can't see. Next village, next town, no. So anyway, control will be there, that control will be less. So for a point charge, what electric field is, which field? Non-uniform field, 7. Then again, next some more I am adding here. Next points I am just writing. You can note down, because textbook doesn't have this point. Then electric field, where it will reach, where it will finish. Electric field. Electric field finishes. See, electric field is going in this direction, right? Where it will finish? Electric field extends till infinity. Electric field from a charged particle extends till infinity, right? Then electric field on the charge equal to 0. On this charge, electric field is not defined. I will say what, not defined. Not defined. That is better. Why we can say not defined? Because what is electric field equation? Electric field is equal to kq by r square. On this charge particle, what is the distance? Distance r equal to 0. If r is equal to 0, it is not defined. Denominator 0, not defined. Now come to the infinity case. If the distance is at infinity, if it is at infinity, electric field is equal to 0. It acts till infinity it will go, at infinity value will be 0. Right? Electric field on the charged particle is not defined. That is all about the topic electric field. So what is electric field? It is a region around a charged particle in which other charged particle experience a force. So the charge which produces field we are calling it a source charge. The charge which experiences force is called known as what? A test charge. For finding the electric field strength at a point, you need to keep, what you need to do? You need to keep a source charge at this point, so that electric field is equal to force by test charge. F is equal to EQ, or electric field strength is given by E is equal to KQ by R square. Coulomb's law, F is equal to KQ1 Q2 by R square. See, some students may have that which equation KQ1 Q2 by R square or KQ by R square. So are two equations. It will be confusing, sir. Don't worry. For force, two charges should be there. But for creating field, only one charge is enough. So the equation electric field KQ by R square. And its important aspects: positive charge radially outward, negative charge radially inward. Equation electric field at a point is given by force on test charge by test charge. Force is equal to EQ. Electric field is independent of test charge. This only depends on what? A source charge. Only depends on DON. Test charge should be small in such a way that it should not alter the electric field of this source charge. Next, electric field is a vector quantity. In a space, it has a fixed, at a point it has a fixed magnitude and direction. Electric field equation kq by r square only applicable for point charges. For uniform field, its magnitude and direction is same. For non-uniform field, its magnitude and direction will be different. This extends to, electric field extends to infinity. At infinity, its value will be 0. Electric field on the charge particle, it is not defined. Ready? So that is about the first topic. Take a screenshot. We are doing the next problem. Only one problem we will discuss in this session. Ready? 1, 2, 3. First question number 1. Board is too good. Okay, whatever the things in this lockdown period, getting this board is a big thing, isn't it? So praise the Lord. So it is a big thing now. In this situation also we are getting enough chalk pieces and this board. Even not adjusting. Before that one big board, a nice smooth board. It's not smooth. Then also whatever you are having now, be happy with that. So question is this one. You are having. Consider at origin you are keeping plus 1 microcoulomb charge. This is plus 1, credit as plus 1. It is not feeling plus 1. That field is not coming. Consider a plus 1 microcoulomb charge fixed at origin. Let P and Q are 2 points on x-axis and y-axis at a distance 4 meter and 2 meter respectively. 4 meter and 2 meter respectively. P and Q are the points on this, on x-axis and y-axis respectively. Question: find the electric field strength at P. Find electric field strength at Q. Shall we start? So starting electric field at P. What is the equation? Electric field. So this charge particle creates a field. So that field equation kq by r square into unit vector r, which is equal to k value 9 into 10 to the power 9 into q value. What is the charge? Who is creating field? Plus 1 microcoulomb plus 1 micro 10 to the power minus 6 kq divided by r square. What is the distance? 2. 2 square 4 into unit vector. Same, you need to find the direction. Here the question is, this is plus 1 microcoulomb charge. So at this point electric field is going away or coming towards. No doubt, since it is a positive charge, electric field moves radially outward. So this is the direction of electric field. In x direction, what is the unit vector? X direction unit vector is I cap. Right? So doing this one, which is equal to 9 into 1, 9 by 4, 9 by 4, 4.5, 2.25. 2.25 into 10 to the power minus 3. Minus 3 in which direction? I direction. Positive I direction. Final answer. Next question, find the electric field at Q. Find the electric field at Q. What is the equation? Same equation, kq upon r square into unit vector r cap, which is equal to k value 9 into 10 to the power 9 into q, same charge particle creates a field. So what is the value? Q value 1 into 10 to the power minus 6 all divided by distance 4 square 60. Right? So 4 by 60 you need to find 4 by 16. Answer you will get 0.56. When you are doing, you will get 0.56 into 10 to the power minus 3. Question direction. What is the direction? Since it is a positive charge, you need to find the electric field at this point. Due to a point charge, electric field radially outward. In which direction? Radially outward, away from the charge. Away from the charge. This is the electric field due to Q. This is the electric field due to P. In which direction? Unit vector J. Y direction, unit vector in Y direction, we can call it as what? J. So answer, this is what? 0.56 into 10 to the power minus 3 in which direction you can. Question number 1. So its B part is given. B part is given. Now you are taking, but you are changing this pointer Q from here to here. This is your Q at a distance 6 meter, and one more modification you are doing. Instead of this plus 1 microcoulomb, you are keeping minus 2 microcoulomb. Question number 2. Question number 2. Question: find the electric field. Find the electric field strength at P and Q. P point you are not changing. Yes. P you are not changing. Find the electric field. Pause the video. Pause the video. Try yourself. Try yourself. By the time I will run this one. Ready? Ready? Yes. Equation. Now this minus 2 microcoulomb is creating a field. So equation KQ by R square, which is equal to K 9 into 10 to the power 9 into charge. See, when you are doing this problem, anyway you are adding this unit vector, direction you are mentioning here. So use the magnitude first. First find the magnitude. Magnitude 2 into 10 to the power minus 6 divided by distance 2 square 4 into unit vector, which is equal to, right? So when you are doing this one, 2 4 cut 2 times 9 by 2 4.5. 4.5 into 10 to the power 3, right? So before in the last problem we were writing, I think we were writing minus 3, right? It is not minus 3, 9 3, it was 3, okay? So the last problem it was answer, you just take the answer 2.25 into 10 to the power 3 not minus 3. Here it was 0.56 into 10 to the power 3. Yes, it was 3 not minus 3 in the last problem, change. Fine. Now you got magnitude 4.5 into 10 to the power 3 into unit vector, right? And to P, what is the direction of this electric field? So it can go, this is the charge particle, it should be in the line joining. Electric field, direction of electric field should be in the line joining of this point and the charge particle. So it can be readily outward or readily inward, in which direction. Since it is a negative charge means electric field will be in this direction towards the negative charge. Towards the negative charge. So in x direction it is plus I. So what is the unit vector in this direction? Unit vector in this direction, that is minus I. That direction positive, this direction negative. So the final answer 4.5 into 10 to the power 3 I minus 4.5 into 10 to the power minus 3, in which direction? I direction. Ready? Next, electric field at a Q. Electric field. Yes, do that one. 9 into 10 to the power 9 into 2 into 10 to the power 2 into 10 to the power minus 6 divided by distance 6 square 36 into unit. So come to this point. Because of this charge particle, one field will be there. That field is always going in which direction? Towards. Since it is negative charge, it is going towards the charge. Electric field is towards the charge, which is equal to say 9 36 4 times 2 4 2 times 1 by 2 0.5 0.5 into 10 to the power 3 unit vector in the direction of electric field. So it is going in this direction. What is the unit vector in this direction? That is your I vector. So final answer 0.5 into 10 to the power 3 in which direction? I direction. This is the electric field strength. Electric field at a Q. Right? That is about this problem example. Now we are going. This is example 1.6. Right? So that is all about electric field starting, electric field concept, important aspects, and its numerical. Next video we will discuss almost all the problems from this electric field topic. So thanks for watching video. We will see in next video. Bye bye.